Welcome back, students, to Chapter 7 Systems of Particles and Rotational Motion. Today, we'll be learning about center of mass of an extended system. So let us just start with two particle system in a straight line. Now look at the pictorial representation here. You can see the x-axis represented in the horizontal direction and the y-axis in the vertical direction, and the origin is O. Now there are two particles here, one of mass m, m1, and the other one of mass m2. So we assume the center of mass to be at C. In that case, the distance of C to the origin is represented by x, and the distance of m1 to the origin is represented by x1, and the distance of m2 to the origin is represented by x2. Now further, the distance of m1 to the center of mass is r1, and the distance of m2 to the center of mass is r2. So these are the representations in this diagram. Now, the formula for x. Now, what is x? X is the distance from the center of mass to the origin. And definitely the center of mass lies midway between m1 and m2. Not exactly midway, it has to lie somewhere between m1 and m2. Therefore, the formula is given as x equal to m1x1 plus m2x2 by m1 plus m2. Now, let us see how we get this formula. Okay, if M2, suppose imagine the second body is heavier than the first body, then the center of mass will lie closer to M2. In that case, R2 will be lesser, R1 will be greater. Okay, we are going to represent that here. If M2 is greater than M1, then R1 will be greater than R2. That means there is an inverse proportionality between mass and the distance between each mass to the center of mass. M inversely proportional to R. If M is inversely proportional to R, then M into R will be a constant, or we can write M1 R1 equal to M2 R2. Now let us make substitutions for R1 and R2. From the diagram, we can make out that R1 is x minus x1 and R2 is x2 minus x. So when you substitute these values in place of R1 and R2 and simplify, you will arrive at x equal to m1 x1 plus m2 x2 by m1 plus m2. This is the formula for the center of mass, the distance from the origin. Now, this is a special case where you can consider M1 and M2 to be equal masses. So, M1 equal to M2. In that case, the formula reduces to x1 plus x2 by 2. Only when the two masses are equal, the center of mass will lie exactly midway between the two masses. Okay, this is now for two particles. Suppose there are n particles in the system along the x-axis itself. Then the formula becomes x equal to m1x1 plus m2x2 plus up to mn(xn) divided by m1 plus m2 plus up to mn. So this can be written in summation form as summation or sigma I equal to 1 to n mi xi divided by sigma I equal to 1 to n mi. Or it can be written as sigma mi xi divided by sigma mi, where of course we know that I represents numbers from 1 to n. Now next is a three-particle system in the same plane, three particles in the same plane. So here we are going to use xy plane as an example here, and we have three particles lying randomly in this plane. where will the center of mass be? So center of mass in a two-dimensional plane, in a plane xy plane, will have coordinates x and y given by x equal to m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. And the y coordinate will be m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. Here again, if the particles are of equal mass, m, that is, if m1 equal to m2 equal to m3, if all three masses are same and they lie in the xy plane, then x will be reduced to x1 plus x2 plus x3 by 3 and y will be y1 plus y2 plus y3 by 3. Thus, for three particles of equal mass, the center of mass coincides with the centroid of the triangle formed by the particles. Now, if there are n particles distributed in space, then x, y, and z, that particles, the center of mass will have all three coordinates, that is x, y, and z. So here x equal to sigma mi xi by m, y equal to sigma mi x yi by m, and z is equal to sigma mi zi by m. Capital M is sigma mi, is the total mass of all the particles in the system. So these particles will be, n particles will be lying randomly in space, in a three-dimensional space. So here the index I runs from 1 to n. Mi is the mass of the ith particle and the position of the ith particle is given by xi, yi, zi. Now let us see what is the position vector of center of mass. Let Ri be the position vector of the ith particle. So what is the position vector? The position vector is the distance of the particle from the center of mass. And capital R will be the position vector of the center of mass. Then we have Ri equal to xi I plus yij plus zik. So you know I, j and k are unit vectors. So I cap, j cap and k cap. So they can be represented in a three-dimensional plane as Ri equal to xi into I cap plus yi into j cap plus zi into k cap. And the position vector R of the center of mass from the origin is equal to capital X. X, Y, and Z are the coordinates of the center of mass. So they can be represented as capital X into I plus Y into J plus Z into K. Here R is equal to sigma mi Ri by M. Next, we will learn about the center of mass of homogeneous bodies. Now, what is a homogeneous body? It is a body with uniformly distributed mass. Here we will study an example of a thin uniform rod. So we have the diagrammatic representation of a thin uniform rod and we see O, the origin is at the center. And if you observe this thin uniform rod, you can see there are particles on the x-axis, positive x-axis, and there are equal number of particles on the negative x-axis also, if origin is at the center. So this is called reflection symmetry. So here the coordinates of center of mass are given by x equal to sigma delta mi by sigma delta mi. So delta mi is a very small mass on the x-axis. Y is equal to sigma delta mi by sigma delta mi. And Z is equal to sigma delta mi zi by sigma delta mi. Now the denominator clearly shows that the denominator is the summation of all the masses that contribute to the thin uniform rod. That therefore it gives the total mass of the system. Now, suppose we increase the number of particles on the x-axis, then the mass becomes smaller. So we can write limit delta m tending to 0. We can write sigma delta mi tends to integral dm, which is equal to m. M is the mass of the uniform rod. We are adding up, when we integrate, we are adding up all the small masses and it will sum up to capital M. In the same way, sigma delta mi xi will tend to integral x dm. Sigma delta mi yi will tend to integral y dm. Sigma delta mi zi will tend to integral z dm. Therefore, the coordinates become, that is, x equal to sigma delta mi xi by sigma delta mi. This will change to, the denominator is capital M and the numerator is integral x dm. In the same way, y equal to 1 by capital M. Capital M is the mass of the entire body. Integral y dm. And z is equal to 1 by capital M integral z dm. So capital X, capital Y and capital Z are the coordinates of the center of mass, or where there are n particles. If center of mass is at the origin of the coordinate system, then r equal to 0. So r is position vector and r is the capital R is the distance of the center of mass from the origin. So if the center of mass lies on the origin itself, then obviously capital R equal to 0. And R equal to, R is equal to 1 by capital M integral R dm. So mass cannot be 0. Mass of a homogeneous system cannot be 0. Therefore, integral R dm equal to 0. And therefore, integral x dm, integral y dm, integral z dm, all these are 0. That is, if the center of mass is at the origin of the coordinate system, then all these terms will turn to 0. By reflection symmetry, for every element dm of the body at x, there is an element of same mass dm at minus x. So, for all the bodies with reflection symmetry, the center of mass coincide with their geometric centers. Now let us work out an example. I'll read out the question. Find the center of mass of 3 particles at the vertices of an equilateral triangle. The masses of the particles are 100 gram, 150 gram and 200 gram respectively. Each side of the equilateral triangle is 0.5 meter long. Okay, let us observe the diagrammatic representation of the problem here. We have 3 particles of masses m1, m2 and m3. And the coordinates of m1 at the point O is 0, 0. It is placed at the origin. We have the second particle at A and its coordinates are 0.5, 0. 0.5 is the x coordinate. So you can see on the x-axis from here to here it is 0.5. It is the side of the length of the equilateral triangle. And since it is on the x-axis, the y coordinate is 0. What about the third one? The third particle is at B and its distance from the axis. Here the x-axis distance is half of the 0.5, half of the side. So it becomes 0.25. And if you work out with a sine theta, sine 60 formula, you will get this distance to be, on the y-axis to be 0.25 root 3. So here we have the coordinates of particles. The particle at O, x1, y1 will be 0, 0. The particle at A, x2, y2 will be 0, 0.5. And the particle at B, x3, y3 will be 0.25, 0.25 root 3. Okay, there is a correction here for x2, y2. It will be 0.50. Here 0.5 and 0. Now you can work out what is the x coordinate and the y coordinate of the particle that is for the center of mass here. This is center of mass. You can see it represented as C. So you know there's a formula x equal to m1x1 plus m2x2 plus m3x3 by m1 plus m2 plus m3. When you work out this formula, you get the x coordinate to be 5 by 18. And y equal to m1y1 plus m2y2 plus m3y3 divided by m1 plus m2 plus m3. So again we get the answer to be 1 by 3 root 3. So the coordinates of the center of mass is 5 by 18, comma 1 by 3 root 3. Okay, the next problem. In the hydrogen chloride molecule, the separation between the nuclei of the two atoms is about 1.27 angstrom. You know 1 angstrom is equal to 10 to the power minus 10 meter. Find the approximate location of the center of mass of the molecule given that a chlorine atom is about 35.5 times as massive as a hydrogen atom and nearly all the mass of an atom is concentrated in its nucleus. Okay, let us read the question again. Hydrogen molecule, so it comprises of a hydrogen atom and a chlorine atom. And the separation between the nuclei of the two atoms is 1.27 angstrom. So we have a separation here as 1.27 angstrom. And so somewhere between them, somewhere closer to chlorine molecule will be the center of mass, C. So we can locate center of mass somewhere in between randomly. Now the distance from H, hydrogen atom, to center of mass we'll consider as x. And therefore the distance from chlorine atom to the center of mass will be 1.27 minus x. The mass of hydrogen atom, if it is m, then chlorine atom mass is 35.5 times the mass of hydrogen atom. So when you make a substitution, m into x equal to 35.5 m into 1.27 minus x. It is like m1r1 equal to m2r2, what we did at the beginning. So when you make the substitution and simplify, you will get x equal to 1.24. So the center of mass of the molecule is 1.24 angstrom from hydrogen atom. Well, that's all for today. So we will continue in the next class. Thank you, students.